In this video, we're going to look at linear maps, sometimes called linear transformations. Linear maps and linear transformations. Again, they both mean the same thing. I'll probably use them interchangeably. Sometimes I'll use linear maps. Sometimes I'll use linear transformations. So consider the vector spaces V and W, a linear map or linear transformation from V to W is a function T such that T has these two properties. Number one, TU plus V equals TU plus TV. Two, TCV is equal to CTV. And these have to be true for all U and V in the vector space capital V, all the vectors in that space, and for all real numbers C of the reals. And sometimes some books, they may make this a more general field, like it might just say not necessarily real numbers. They might have a general field which includes, possibly complex numbers. But I'll just keep it as real numbers right now. So again, if the function obeys these, you put two vectors in, add them together, is equal to them being transformed separately. And if you multiply by a constant, same as constant times the transformation, that works for all vectors and all constants, then it's a linear map. Now, we can also, this can be simplified. So we can say it this way. T is a linear transformation. Again, say from the vector space V to W. If T CU plus V is equal to T CU TV, once again for all U and V in the vector space V, and for all C in the reals. So you can use either of these tests, either this test up here, it has a couple of steps to it, or this one-step test down here. You pretty much end up doing the same work, even though this is one step and this one is two, you'll kind of end up going through the same process if you use either one of these. And now if you have a matrix, you can turn a matrix always into a linear transformation. So let me show you what I mean by that. Suppose A is any n M by N matrix. If we define a transformation, say we put in maybe an X, it could be a matrix. Let me keep it like, say, just to a vector X, let's say. And let's say we define our transformation this way. Then T is a linear transformation. And you can show this pretty easily. I won't do that here. So a matrix can always be turned into a linear transformation by defining it this way. Put in, of course, obviously the appropriate vector of the right length to match the matrix, so you can multiply it, and then this is going to be linear transformation. And also consider, say, the integral. Consider, let's say you put in a function. Let me sort of write it. What would be the good way to maybe put it in like this? So it's a function, let's say, of x defined by, say, 0 to x f t dt. So your transformation is you put in a function and then you integrate it. Is this a linear transformation? And so let's test it. Let's test using that second test that we had up here. We're going to put in a cu plus v. And I should say, again, in this one where f is a continuous function. Let me throw that in. And so let's see if we can prove this. Once again, we're going to do that second test. We're going to, so let f and g, those are going to be our vectors, be continuous functions. And c is a real number. If we take, remember what our test was, we take c times the first vector plus the second vector like this. Remember, when we get into the general terms, like say vectors aren't vectors in the normal sense all the time. In this case, our vectors are continuous functions. So let's try this again. Remember, we eventually want to show that TCF, this is equal to CTF plus TG. And so we'll go through the process to show that. So we want to, what we do, of course, just go through the steps, put this into our integral here. And so we're going to replace this with this. I'll leave off the t just for clarity. And again, remember what we eventually want to get to. We want to eventually get to something that looks like this. So now, usually what you do to do that, so we have a definition of our transformation, and we usually try to work with the properties that this definition has. So we'll be working, say, with the integral property. Now we know if we're integrating and we're integrating two things we add together, remember, by the properties of integrals, We're allowed to do that. And also, by the property of integrals, remember, if you have a constant times a function, you can always factor out that constant. Like that. And now what do we have here? What is this here? This is going to be C times a transformation F, because look how this is defined. This is the same as this. So this is TF. And then this over here is TG. So we started with this. We ended up with this. And so, yes, this is the linear transformation. So I'll do some more examples at the end of the video. I won't fill in too many here because we're going to have some other ones sort of along the way. But if you want more, you can look just at the end of the video, this video. So let me deal with some other things. Let's talk about the null space of a linear transformation. Like I said, linear transformation or linear map. Again, I'm going to use it interchangeably. Sometimes I use one, sometimes I'll use the other, depending on which you're used to. You can pick whichever one you like. So the null space linear transformation or linear map T from some vector space V to some vector space W is the subset of V such that, and I'll write it in this term here. A lot of times I'll just call this null. The null space of T is going to be those values, say V in the space V, such that when you put them into the transformation, you get 0. So the null space is specifically those values that make the transformation produce 0. Now notice it says here that these values are a subset of V because we're considering these values here that we're putting into the transformation to produce 0. And they're producing 0 over here in W, but we're interested in what values, what vector caused that. And so it's a subset of V, and there's also a theorem that we can say the null space of T. Once again, let me put all the details in. We have the null space of T is a subspace of the vector space V. Not only a subset, it's a subspace. And let's prove that. Once again, let U and V be two vectors in the null space of T. And once again, let's make C to be a constant and R in the reals. So let's go through and show. Remember, now we're going back to subspaces, which uses very, very similar test to what we had. We need to let this be in here, this be in here, and we need to show, remember, to show a subspace, which was previous videos, we need to show that C V plus W is in that null space. So we're picking a couple vectors in null space. Remember, again, this is not the linear transformation test. So it looks very similar, but this is the subspace test. We have to show that that's in the null of T. So we need to show that true. So let's go through and do that. So we're going to put this into CV plus W. Again, this can look a little bit confusing because it looks very similar to when we're testing for linear transformation. But now, because we know T is a linear transformation, let me put this here, we can say that T CV plus T of W. Again, because T is a linear transformation, we're allowed to do this. Then next thing, we can say we can factor this out. C TV TW, once again, because T is a linear transformation, we can do this. And now, remember, V was in the null space of T, so this is going to be 0. And W, oh, excuse me, I'm sorry. I should have originally, could you fix this? I should have made the VW. Sorry about that. Back here, I should have made this V and W. Sorry. So I want to pick two vectors, V and W in the null space. C is an R. And now we need to show that's a null space. So again, V was in the null space. W is in the null space. So this is going to be 0. And so this is going to be 0 plus 0 is equal to 0. So that means CV plus W is in fact in the null space of T. Therefore, the null of T is a subspace. Now going on to another definition. A linear map T V to W is called injective, or one-to-one. If whenever U and V are in V and TU equals TV, then U equals V. It's the same definition of one-to-one or injective that you had for functions. If you get the same, if when you ever get the same function values for supposedly two different vectors, if that only occurs only when the vectors are the same, then the function was one-to-one. In what we're dealing with here, it tells us the linear map is one-to-one. And let's look at a theorem. A linear transformation say T from V to W is injective. One-to-one. If and only if the null space of T is equal to 0. So linear transformation is one-to-one or injective if and only if the only thing that's in the null space of transformation is 0. So let's see if we can prove this. So we have to prove it two ways. Remember, if it says if and only if, we have to first start with one of the assumptions. Like say in this case here, we'll start by assuming the null space only has 0 in it, and then prove it's one-to-one. And then we have to go the other way, assume it's one-to-one, and prove the null space is 0. So let's suppose the null space of T only has the vector 0 in it. Then furthermore, so we're again assuming this is true, then also suppose that you have this for some U and V in V. So let's assume this. Now we need to show that U and V are the same. So let's go through this. So if we start with this, let's rearrange this. Just say T U minus TV is 0. So I just brought that over to the other side. And again, remember, because of the rules of transformations, we're allowed to say this because we do have a linear transformation. U minus V is 0, like this. So now what does this mean? Since we have TV minus V is 0, this implies that U minus V is in the null space. So U minus V is in the null space of T, but remember what we have up here, the only thing in the null space is 0. But the null space of T just has a 0 vector. So that means that U minus V has to be 0. Then that means U equals V, what we're trying to show. Therefore, T is injective or 1-to-1. So we started by assuming when I had 0 in the null space and was able to prove that that implies T is injective. Now let's go the other direction. Suppose T is injective. Now we want to show that the only thing in the null space is 0. So we're going to further suppose that there exists a V in the null space of T. Just could be any vector V. So what that means is then TV is equal to 0. And of course, and we also know that T0 is also going to produce 0. Therefore, we have TV is equal to TO. But since T is injective, again, or 1-to-1, then V is 0. So we assume V was in the null space, but don't think it could be a 0. Therefore, the null of T is 0. So let's talk about some definitions next. Let me mention the nullity of T. So the nullity of T is the dimension of the null space of T and another definition. The rank of T, again, we're talking about linear transformations. Rank of T is the dimension of the range of T. And let me throw one more thing in here. Suppose A is a matrix. Then the rank of A is the number of linearly independent rows or columns of A. So there's actually a couple of ways. We'll see how they're connected here in a minute. So the rank of a linear transformation is the dimension of the range of that linear transformation, but also the rank of a matrix is the number of linearly independent rows or columns. There always will be the same of A. So let's look at a couple of examples here. I'll take a very basic example. So consider this linear transformation. Say we put in a vector ty, like this. So let's consider this linear transformation where this is really kind of a linear transformation using a matrix. You can kind of consider this your matrix A and find the null space of this transformation and the range of T. Also, we'll find the nullity of T and the rank of T. So let's take a look at this. So we have, say, something like this. Py. Let's multiply this out. And we want to find out when this is going to be 0. Because we want to find what the null space is. So we want to set this equal to 0, which means those two are 0. So what does this mean? This means x minus y is 0, negative x plus y is 0. So we're going to be working with these two. But if we multiply this say the second equation by -1, we'll have something like this, huh? I multiplied this equation here, times -1, we get this. So we really only have one equation, right? So only one equation, are both the same. So what is going to make this 0? So we get the 0, 0 vector when x is equal to y, or y equal to x, however you want to say it. So any vector of the form you could call this x, x, or y, y. Any vector of this form is going to be in the null space of T. And of course, you can get any vector in this form by having a basis of 1, 1. Like this, huh? Because you could multiply this by any constant you want to get something of this form. So this is the basis. And now, since the basis of the null space has just one vector, the dimension of the null space of T is 1. Or, as we said a few minutes ago, the nullity, it's called, if T is 1. So what about the range of T? Again, we could probably do this in many different ways, but you can even sort of say work with this sort of logically to see, what kind of values can you get from this. Once again, let's go back to so again, what about the range? So this time, again, we just keep our general vector. So let's go back to what we had before. Let's say if we multiply these out, this time we're not looking for just 0 over here. We're just kind of making this more general, seeing what kind of values are we going to get out of this. And again, you can probably look at that and figure it out. But let me kind of go through this more, a little bit more intuitively. So let's just pick some vectors. Pick, I don't know, say 1, 5. Maybe pick 1, 5 in here. And so if we put in 1, -1, -1, 1, 1, 5. And what do we get here? This is going to be 1 -5, -5 plus 1. And this is going to be -4, 4. And you could maybe pick, let me pick another one here. Let me just pick minus 8, 2. And I won't go through it, so I'll just put them up here. And what's that going to give us? Minus 8, minus 2. What's this going to be? Minus a minus 8 plus 2. That'll give us minus 10 and 10. And let me pick, I don't know, pick 5 and 3. 5 minus 3 minus 5 plus 3 is going to give us 2 minus 2. So you're pretty much seeing what we're going to get out. The range is always going to be, whatever the x value is, the y value is going to be just the opposite. So the range of t is of the form x minus x. Or you could call it minus xx. You get the same thing. So the basis for the range, once again, you could pick, vector, say like this. Or you could pick negative 1, 1. Could you multiply by anything you want, any constant to get any values like this you want. So again, the dimension of the range of t, since there's only one vector, is 1. And then the rank of t is 1. We said by definition, the dimension range of t is the rank of t. And actually, for I plotted these here. Let me just show you a minute here what I have. So I plotted the null space here. Remember, null space was vector form x, x, and the basis was 1, 1. I just plotted that along here. So this is the null space. And then the range, remember that was x minus x, and it had a basis of 1 minus 1. I plotted those here. So just to give you a pictorial view of that. And let's also do one more thing. So far we found that the rank of t was 1, the nullity of t was 1. And what if we had just worked with the matrix? So again, what was our matrix? It was 1 minus 1 minus 1, 1. That was our matrix. And what's the number of linearly independent rows that we have? Notice and you could do like Gaussian reduction if you wanted to, whatever. Notice that if we multiply second row by -1, we get the first row. So we only have one linearly independent row. And you would have gotten the same thing if you work with the columns. Let me just put that in parentheses. So the rank of A was equal to 1, which same thing we got when we worked with just the linear transformation. And another thing to notice from this last problem, and actually let me give you another theorem. Let once again V and W be vector spaces. Over the real numbers. Let's say reals. And let T from U to W be a linear transformation. And suppose V is finite dimensional. And just have to say that because this next thing wouldn't make sense if it was not. Then the dimension of V is going to be equal to the rank of T plus the nullity of T. And again, from our last example, notice that worked out. The dimension of our vector space V was 2 because we're putting in 2-dimensional vectors. And then we said the nullity of T was 1. And the rank of T was 1. So the dimension of V equal to the rank of T plus nullity of T. That all worked out because this was 2 and it's 1 plus 1. So that worked out. So that's pretty much all for the theory. And I'm going to just do a couple more examples I mentioned before. Again, if you don't need to see more examples, you can stop watching this. But although these next 2 examples I think are pretty interesting. So let T be a linear transformation from, let's say, their n by n matrices. That's what kind of this notation means. Defined by TA AB minus BA, where B is a fixed n by n matrix. Is this a linear transformation? So again, remember, so these are like, again, this means n by n. So basically, these are square matrices. You're putting in a square matrix, you're getting out square matrix, same size. B is a fixed n by n matrix, also the same size. So is this a linear trend? Let's do our test. So proof, let A1, A2 be n by n matrices. And let C be a number in the reals. And so let's go through our normal process. Again, when I say there's a linear transformation, remember we put in then this TCA1, A2. And remember, we want to show when eventually shows CT, this is equal to CTA1 plus TA2. So again, let's try this. So we're going to do, we'll put this into our definition. Like this. And now let's just use our normal, matrix multiplication. And we want to sort of arrange it a little bit better. Let me move this C out. Remember, we're allowed to do this. Remember, it's one of the rules of matrix multiplication. If you have a constant, like in between these two, you can factor that out. Now, keep in mind, we want to try to do, remember, we want to try to get a C times TA1. So we want to probably put the terms with A1 together. Like this. And then we can factor out our C. like this. And now what is this? According to our definition up here, this is precisely CTA1, isn't it? And this over here is precisely TA2. So we started with this, we got this, therefore T is a linear transformation. And let's do a couple more. We're going to go back and deal with functions again. Define this linear map, where say this is a space of functions. We have this, and then our transformation so we have our function, and let's say it's a function of x. I'm going to leave the x off. Maybe just at the beginning here, I'll put it in, Val. Just for clarity later, I'll leave off. So the transformation is our squaring our function. Is T linear? Is it a linear transformation? So again, as usual, let f and g be continuous functions. And c is in the real numbers. And put those in. Remember, we're going to eventually show that c, this is equal to CTF plus TG. So let's go through and square this. Again, I'm leaving off the x just for clarity. Then what are we going to get in the middle? We're going to get CFG plus GCF plus G squared. And let me just clean this up a little bit. CFG. Now we can bring this C out. And also, the functions commute. So we can call this CFG plus G squared. And let's see if we can try to rearrange things a little bit. Remember, we want to get CTF. So let me just rearrange these. This is going to be F squared. This is going to be G squared. This is going to be 2CFG. And of course, what is this? This is going to be C squared TF. This is going to be TG plus 2CFG. It looks like it's not going to work. So we don't get CTF plus TG. We first of all get a C squared here. And plus we get all this other stuff over here. So no. T is not a linear transformation. So finally, let's do one more. That T, again, this means n by n matrix to the real numbers. Defined by TA equals the trace of A is T a linear transformation. And so let's try this. Let A and B, you can say B, n by matrices, or you just say it's in that, using that symbol like this. And C is in R, real number. Then let's try this, CA plus B, and see what we get here. So according to our definition, we want the trace of CA plus B. Now remember, the trace is the sum of all of the diagonal elements. So let's think about this for a minute. Let me just, probably don't need to do this, but let me just maybe show what we mainly have here. So this is really saying, so we have, say, A11 plus B11. Let me just maybe make this a little bit bigger. Yeah, normally you don't have to show this if you have a good understanding what trace means. So we want the trace, and we only need to show the diagonal elements because remember that's what the trace is. So this is 1, 1, B1, 1. Then the other ones don't really matter. C, A2, 2, B2, 2, because we're going to add these two matrices together. First multiply A by this, add them together all the way down to CANN, BNN, like this. The other ones aren't going to matter. So again, remember the trace is the sum of this. And so that's going to be the sum from I equal 1 to N, just of the diagonal elements here. And so that's going to be CAII plus BII. Because again, those central elements always have the same two indexes. Now again, using the rules of sums, we can break those apart. And furthermore, once again, with sums, remember, if you have anything here that does not have an index in it, you can factor it out. Like this. Now, remember, what is this? This is just a sum of all the diagonal elements of A. So this is precisely the trace of A. This is the sum of all diagonal elements of B. So that's what the trace of B. And of course, from our definition of our transformation, the transformation is defined as the trace. So we're going to have here is going to have the constant C times the trace of A, which is defined as our transformation, plus the trace of B, defined this way, like this. So we started with transformation of this and ended up with CTA plus TB. So yes, T is a linear transformation. And notice how we did all of these tests for linear transformations. We, put the C A plus B in, again, it could be in vectors, C, V plus W, or it could have been C with red function, CFG, and then use the definition of a transformation and then worked with whatever elements we had. All of a sudden, this turned into sums. So we had to use our properties of sums. The fact that you can break them apart like this, the fact you can factor out anything that doesn't have an index letter in it. Or before we were dealing with functions, with integrals, we had all the rules of integrals. So you use whatever rules you can use here, then kind of bring everything back to get it back in the form of transformation. That's the way we did all of these.